So this lecture is about polymers and fibers. Before we can understand how polymers and fibers can be used in forensic science, we first need to know a bit about the chemistry of polymers and fibers. So what is a polymer? Well, if you take a small molecule and then you link it to another one of the same small molecule, and then to another one, and then to another one, and then to another one, and so on, you end up with a long chain molecule made up of those original single molecules linked together. So those original single molecules are known as the monomer, and this long chain molecule is known as a polymer. Poly, of course, comes from the Greek for many. Now, not all polymers consist of the same monomer over and over and over again. We can mix up different monomers. For instance, if you have two different monomers, then when you link them up to make a polymer, you can get what we call a copolymer, where the two have been combined to make a single long molecule. The main thing to understand is that a polymer is made up of long chains of these individual monomers. So here's an example of a very common polymer that we all encounter every day in our lives, and that's polyethylene, which is better known as polythene. So polythene is the polymer derived from the gas ethylene. So every year, millions of tons of ethylene are polymerized to make polythene for all sorts of uses, including, of course, things like shopping bags. We're also familiar with polymers like polypropylene and polystyrene. Polystyrene, of course, is the material that's used to make styrofoam packaging. And these are polymers from the corresponding monomers, propylene and styrene, and it's done in a quite similar way to the polymerization of ethylene. Now, polythene, polypropylene, polystyrene are widely used to make all sorts of things, but they're not actually good for making fibers. So people don't make fibers out of these particular polymers. Here's a polymer that is excellent for making fibers. It's nylon. And nylon is a copolymer where you take two quite different compounds and induce them to form a chain. So nylon 66, there are different forms of nylon, but nylon 66 comes from adipic acid polymerized with diaminohexane. And if you count up the atoms, you'll realize that molecules of water are being produced as a byproduct. It's nylon 6,6 because adipic acid has 6 carbon atoms and diaminohexane has 6 carbon atoms. And you can see it forms a polymer where you have alternating adipic acid and diaminohexane units. And nylon, as I mentioned, is an excellent polymer for making fibers. And probably at this very moment, all of us are wearing something containing some nylon. So suppose we have a fiber found at a crime scene. What can you do with that fiber to identify it? Well, the simplest thing you can do is just to look at it under the microscope. And this may help you determine the type of fiber. For instance, whether it's wool or nylon or cotton or some other. Now, because we can consider fibers as organic chemicals, we can also use on them the spectroscopic techniques that we studied in an earlier lecture. So you can use spectroscopy on the fibers to determine their chemical composition. Microscopy, you can also look at physical features such as the shape of the fiber. Now, some fibers, specifically the synthetic fibers, the shape is characteristic of the manufacturing, which we'll talk about in a moment. Now, most fibers are going to be colorless. Most synthetic fibers will originally be colorless, but we like to have colored fibers in our clothes. So a dye has to be added to these synthetic fibers to give them those colors. So not only can we do spectroscopic analysis to determine the chemical nature of the fiber, we can also do spectroscopic analysis to determine the chemical nature of the dye. And this, of course, will be another step towards individualization of that fiber. The manufacturers also add other chemicals to the fibers to make them attractive for use in clothing. For instance, one kind of chemical that's added are called delustrants, and these are to make the fibers less shiny. So again, we can use chemical spectroscopic methods to identify the delustrant. And the more different chemical components of the fiber that we can analyze, then the better we can get towards individualization of that fiber. Obviously, there's going to be a difference between natural fibers and synthetic fibers. Natural fibers coming from plants and animals, synthetic fibers coming from the chemical industry. So let's take a quick look at making synthetic polymers and synthetic fibers. Synthetic polymer fibers are typically made by a process called extrusion. So on one side of a barrier, there is the polymer either in its molten state or in solution, so it's a liquid form. The barrier is permeable, there are holes in it, so when the liquid form of the polymer is forced through the barrier into a new medium where it solidifies, as it goes through these holes, it will form fibers. And this is called extrusion. And synthetic fibers are typically made by extrusion processes. So clearly, the shape of the fiber and the size of the fiber are going to depend on the hole that the material was forced through when the fiber was formed. This will vary from manufacturer to manufacturer. So if you have a synthetic fiber, you can look at it under the microscope, and the shape of the fiber will help you to identify which manufacturer and perhaps which batch of material when it was made. I mentioned that we can also identify the chemicals that make up the fibers using spectroscopic methods. And a very good method for doing this is from the infrared spectrum. Now, the normal infrared spectrum is recorded on a fairly large amount of material, but a fiber found at a crime scene would be just a single fiber. So we have to use what is called an IR microscope. And this combines a microscope, that is so you can see the fiber, and the IR spectrometer. And this combination of the IR microscope allows the analysis of the chemical constituents of the fiber. So this is the infrared spectrometer that I use for lecture demonstrations. Most infrared spectrometers are very sensitive machines and you can't move them, but this one's very robust and I can pick it up and carry it across campus and use it for lecture demonstrations. It's not the kind of machine that a forensic scientist would use for fiber analysis, and that's because it's just an ordinary infrared. It's not an IR microscope. So we're not going to be using the tiny little fiber samples that might be collected at a crime scene. We're going to be using some slightly bigger pieces of string. So I have two samples here. One of these is genuine wool. One of these is synthetic wool. And an ordinary person, just by inspection, really wouldn't be sure which one was which. But we're going to use the infrared spectrometer to prove the identity of these two. This machine here works by reflectance. The IR beam is generated inside here, and it reflects off this little window here. And so what we're going to do is press the sample against that little window. So this is the IR spectrum of that first sample, and an important band to look at is this one here. We can see a strong absorbance at 1624 wave numbers. And we know that this kind of absorbance is characteristic of the stretching of the carbon-oxygen bond in a protein. Now, wool, of course, is a protein. Wool is made of protein. We can conclude that this sample is the genuine wool. Now let's analyze the second sample. So if we look at the IR spectrum of the second sample, which is the green trace on the screen, we can see there's a similar absorbance, but it's shifted. We can now see that the carbon-oxygen stretching absorbance is coming at 1729. This is not where you expect to see this absorbance when you're dealing with a protein. So clearly this second sample is not real wool, and it probably is polyester. But if we look a little bit further at the spectrum, we can see there's another band just here at 2241. And what this is telling us is that this fiber sample is probably some kind of blend of different polymers, and this second absorbance here at 2241 is probably a nitrile polymer. Our infrared spectrometer is not limited to analyzing fibers. We can analyze just about anything that we can put into that sample holder. So here I have $2, 2 Singapore dollars. Now, money is normally made of paper, but this is not. This is a polymer note, and we can analyze this using infrared. This is the spectrum of the Singapore $2 note, and you can see that it shows an absorbance at 1714 wave numbers, which is quite similar to the polyester. So these banknotes are not made of paper, they're made of polymer, and it's telling us that at least one of the polymers in this banknote is quite similar to that second fiber sample. So this is the Singapore $50 note. So let's use infrared spectroscopy to find out what this is made of. So if I put the $50 note so the red trace is the spectrum of the $50 note, and you can see that there's almost no absorbance in the region about 1700 wave numbers. But there's a big absorbance in the region about 3200 to 3300 wave numbers. This is because our $50 note is still made of paper. Paper is made of cellulose. It doesn't have any C double bond O bonds in its molecule, so there's no absorbance in the same area where we saw the polyester absorbing. But cellulose has lots of hydroxy groups with OH bonds, and these absorb in that region above 3000 wave numbers, and that's what's responsible for this absorbance that's indicated at about 3200. So using the infrared spectroscopy, we can very quickly tell what these different things are all made of. Here's one example of a case where the IR spectrum of a fiber proved to be very important. And this is the case of a US Army officer called Jeffrey McDonald, who was stationed at Fort Bragg, North Carolina. And he was convicted of murdering his wife and daughters, and they were killed by being beaten and stabbed in the night in their own home. Now, McDonald's defense lawyers came up with the defense that the murders were not done by McDonald himself, but they were done by a group of drug addicts who had broken into the house. Problem was, at the original trial, there was no evidence that anyone else other than the family had been in the house. So the defense here is trying to raise reasonable doubt, but without evidence that there were other intruders, this was not considered to be reasonable, and MacDonald was found guilty. However, the defense did find additional evidence which they used at the appeal. And that evidence was a fibre from the crime scene which the defense said did not match any of the clothes of the victims, and therefore is evidence of an intruder. Well, the way to confirm that this fibre did not match any of the clothes was by doing IR spectroscopy of all the clothes. This was done by the FBI, and here is one result. The lower trace shows the infrared absorbance spectrum of this fibre, which the defense is claiming is from the real attackers. The upper trace is the infrared spectrum of fibres in a fall belonging to one of the victims, Mrs. MacDonald. And you can see that the two traces match very closely. So this is not evidence of any intruders, because it could be just from the item of clothing belonging to Mrs. MacDonald. The appeal was not successful. Many polymers that we use are actually natural materials. And one example of a natural polymer that has been used for many decades, many centuries, is rubber. And rubber, which comes from the rubber tree, is a polymer of the chemical isoprene. And that polymerization is actually done by the tree, and the crude latex, which is a very sticky liquid form of the polymer, just drips out of the tree when it's cut in the right manner. Rubber, of course, has been used for clothing. It's much better for boots rather than clothing, and it's not a good material for making fibers. One of the best natural materials used for making fibers is cellulose. Now, cellulose is a polymer of glucose, and glucose can polymerize in nature in two different ways. It can polymerize to form starch, which we can digest. We eat it every day in potatoes or rice or bread. And if it polymerizes in a slightly different way, then it forms cellulose, which is the principal structural material for all plants. And that cannot be digested by us. The difference in the way of polymerization is simply what we call stereochemical. It's a small difference in the three-dimensional structure of the polymer. So cellulose, the structural material for plants, can be a very good natural polymer, particularly from the cotton plant. And cotton, of course, is one of the major materials that's used for making clothing. The fibers are produced naturally by the plant, and then they are spun and they are processed by the mills. In forensic terms, cotton is a problem because all cotton fibers are chemically identical. They are all cellulose. In addition, because they are a natural fiber and they're not produced by any chemical means, they pretty much all look the same. All cotton plants give fibers that are very similar. The differences with cotton come in the later processing in terms of when it's dyed. So if you have a cotton fiber from a crime scene, the most information you're going to get is from the dye. That means if you're going to commit a crime, the best clothes to wear are those made of white cotton. Another important class of natural polymers, more important than polymers of glucose, are the proteins. Now, there are about 20 amino acids which are essential for life. And the amino acid molecules all contain what we call a carboxylic acid group, CO2H. Adjacent to that, they all contain an amino group, NH2. One exception, there's one exception that does not. These two factors are constant. The 20 or so essential amino acids differ in the remaining substituent, which I've indicated as R. And that is what makes these amino acids different from each other. The polymers are formed by the carboxylic acid unit of one amino acid reacting with the amino group of another, and so on, making a chain. And you can create an extraordinary number of proteins because you can combine the different amino acids into all sorts of different sequences depending on which of these substituents are you choose and what combination of different substituents are you choose down the chain. The R substituent makes all the difference, and the structure and the function of the polymer depends on those substituents. So while cellulose is the structural material for plants, proteins are the structural material for animals. They provide our tissues, they provide our cells, they provide our hair. Hair is made of protein. They provide our fingernails. And they are part of our bones. Even though we say our bones are made of calcium, actually our bones are made of calcium phosphate combined with proteins. Our enzymes, that is, the chemical catalysts that keep our biochemical machinery running, these enzymes are also proteins. They're very highly specialized proteins. And the antibodies that we talked about in our lecture on blood, these are also proteins. So our bodies use proteins for so many different functions. And our body can do this because these different R substituents on the amino acids gives us an enormous number of possible proteins.